Hello, everyone. Welcome to my session, IoT Risk Management. My name is Manikirti Nagotu, and I'm a cybersecurity professional. I specialize in cybersecurity strategy, incident response, risk management, security training, and awareness programs. So let's look at the agenda. So for today's session, I will be briefly speaking on what is an IoT device, NIST guidance, IoT applications, associated vulnerabilities, IoT risk mitigation goals, risk management overview. All the discussions are from the perspective of IoT devices used in organizations, and majority of my session is based on NIST guidance, which is publicly available. Also, I will be discussing the topic from risk management perspective and establishing IoT cybersecurity requirements. This would not cover the IoT guidance for manufacturers, which is covered under NIST 8259 series. So the total Internet of Things market worldwide was worth around $389 in 2020 and is forecast to rise more than $1 trillion in 2030, more than doubling its revenue in 10 years. If we look at the drivers for the growth of IoT, high-speed connectivity, low-cost technology, and increased cloud adoption are some of the reasons. I would briefly discuss about IoT applications in different industries in the next slide. The trend that we're seeing most of the times, IoT devices are integrated into organizations' environment without evaluation of the device security capabilities. The unique aspect or difference between IT devices and IoT devices is heterogeneity. IoT devices lack the functions as traditional IT devices, which in turn creates security challenges to organizations. In general terms of cybersecurity objectives, confidentiality, integrity, and availability are important for IT devices. Confidentiality often receives the most attention for conventional IT devices because of the value of the data and the consequences of breach of confidentiality. For many IoT devices, availability and integrity are more important than confidentiality because of the potential impact to the physical world. Many IoT devices cannot be accessed, managed, or monitored in the same ways conventional IT devices can. The availability, efficiency, and effectiveness of cybersecurity and privacy capabilities are often different for IoT devices than conventional IT devices. The benefits that come with those deployments similarly cross industries. Typical return on investment includes the following: lower operation cost, enhanced productivity. So let's look at some of the IoT applications. So how does IoT find applications, or where are they used? Manufacturing. IoT is important in manufacturing industry because it automates operations. The operational technology in a smart factory includes programmable logic controllers, industrial IoT devices, distributed control systems, embedded systems, and more. Agriculture. Data on soil moisture, chemical applications, livestock health, and information allows farmers to track farm operations in real time and make better informed decisions on improving farm productivity and performing preventive maintenance. Healthcare. Just to quote a few, with the help of IoT solutions such as real-time remote health monitoring devices, wearable smart pills, diabetes management systems, and more, it has become easier and more efficient to monitor a patient's health conditions and make treatment decisions. Transportation. For example, through IoT-based safety solutions, vehicles can communicate any incoming accidents and bad weather conditions. So in general usage, you would see smart TVs, smart speakers in office, smart devices which can be misused for listening and gathering confidential data. That is the challenge that we have with IoT devices. What is prompting this change to use IoT devices? Data analytics, automation, connectivity, and remote monitoring have become part of the business operations, and it's very much needed right now. So let's look at the NIST guidance. So as mentioned in the introduction slide, our session is focused from risk management perspective and establishing IoT cybersecurity requirements. This will not cover IoT guidance for manufacturers, which is covered under NIST 8259 series. So the IoT Cybersecurity Act of 2020 requires NIST to provide guidance on the appropriate use and management of IoT devices. NIST 8259 series provides guidance for manufacturers and they're supporting third parties to sell and support IoT devices for customers. These reports define the baseline cybersecurity capabilities for IoT devices from analyzing international standards and guidance. Standard Publication 800-213 series addresses the needs of federal agencies seeking to deploy IoT devices within their systems. NIST Risk Management Framework is the foundation for IoT guidance as well. 800-213 explains the role of IoT devices as elements and provides guidance for addressing the unique risks IoT devices can present. 800-213 is complemented by 800-213A, the IoT Device Cybersecurity Requirements Catalog. It is a collection of technical and non-technical cybersecurity controls, defining a broad range of IoT device capabilities and supporting non-technical actions that an organization can apply in documenting their IoT cybersecurity requirements. Consumer IoT products. This guidance was developed with the intent to develop product-focused outcomes that enable consumers to make informed decisions about purchasing and maintaining IoT products. So let us look at IoT device capabilities. What does a typical IoT device look like? The IoT device generally can have at least one transducer, that is sensor or actuator, for interacting directly with the physical world, and at least one network interface, example Ethernet, Wi-Fi, Bluetooth, Zigbee, for interacting with the digital world. The sensor that transmits data cannot function on its own. Some IoT devices may be dependent on other devices, example an IoT hub, or systems, example a cloud, for some functionality. IoT devices will be used in systems with many IoT devices or maybe IT equipment. Each IoT device provides capabilities, features, or functions it can use on its own or in conjunction with other IoT and non-IoT devices to achieve one or more goals. This is not a comprehensive list of all possible IoT device capabilities, but just an example. So transducer capabilities interact with the physical world and serve as the edge between digital and physical environments. Every IoT device at least has one transducer capability. Sensing, example, temperature measurement, and actuating, example, electronic door locks, are two types. Interface capabilities enable device interactions, example, device-to-device communications, human-to-device communications. Application interface, human user interface, network interface are some of the other things. Supporting capabilities provide functionality that supports the other IoT capabilities. Example are device management, cybersecurity, and privacy capabilities. So let us look at the cybersecurity and privacy risk considerations. So IoT devices generally face the same types of cybersecurity and privacy risks as conventional IT devices, though the prevalence and severity of such risks often differ. For example, data security risks are almost always a significant concern for conventional IT devices. But for some IoT devices, there may not be data security risks because they do not have any data that needs protection. Risk one. Some of the examples of how IoT devices interact with the physical world is different. Some of the IoT devices with actuators have the ability to make changes to physical systems and thus affecting the physical world. IoT network interfaces often enable remote access to physical systems that previously could be accessed only locally. Another important aspect of IoT device interactions with the physical world is the operational requirements devices must meet in environments and their use cases. Many IoT devices must comply with stringent requirements for performance, stability, reliability, resilience, safety, and other objectives. These requirements may be at odds with common cybersecurity and privacy practices for conventional IT. In terms of general cybersecurity objectives, as I've already mentioned, confidentiality is more focused for conventional IT devices because the value of data and the consequence of breach of confidentiality. For many IoT devices, availability and integrity are more important than confidentiality. An attacker who can view the IoT devices stored or transmit data might not gain any advantage or value from it, but an attacker who can alter the data might trigger a series of events that can cause an incident. So if we look at the risk consideration too, in general for IT devices, you determine the authorized people, process, and access management. In other words, an authorized administrator manages the IT devices operating system, and applications. In contrast, many IoT devices are opaque, often referred to as black boxes. They provide little or no visibility into the state and composition, including the identity of any external services and systems they interact with, and little or no access to management of their software and configuration. Some of the specific aspects to IoT devices are differing lifespan expectations, unserviceable hardware, heterogeneous ownership. So, what do I mean by heterogeneity? So, for example, an IoT device may transfer data to manufacturer provided cloud based service processing and storage. Data may also be sent to a cloud service to aggregate data from multiple devices in a single location. These cloud services may have access to portions or all of devices' data, or even access to and control of the devices themselves for monitoring, maintenance, and troubleshooting purposes. In some cases, only manufacturers have the authority to do maintenance. An organization attempting to install patches or do other maintenance tasks on an IoT device may void that warranty. Also, in IoT, there may be little or no information available about device ownership, especially in black box IoT devices. Another concern with heterogeneous ownership is the effect on device reprovisioning. What data may be still available after transferring control of a device? So, if we look at the last risk consideration, many IoT devices do not or cannot support the range of cybersecurity and privacy capabilities typically built into conventional IT devices. For example, a black box IoT device may not log its cybersecurity and privacy events, or may not give organizations access to its logs. The level of effort needed to manage, monitor, and maintain pre-market capabilities on each IoT devices may be excessive. So let's look at the risk mitigation goals. So NIST guidance tells us that cybersecurity and privacy risks for IoT devices can be thought in terms of three high-level risk mitigation goals. Protect device security. So this focuses on using a device to carry out attacks. Example, distributed denial of service attacks against other organizations, and eavesdropping on network traffic or compromising other devices on the same network segment. So this goal applies to all IoT devices. Protect data security. So protect confidentiality, integrity, availability of data, including PII collected by, stored on, or transmitted to or from the IoT device. This goal applies to each IoT device except those without any data that needs protection. Protect individuals' privacy. So protect individuals' privacy impacted by PII processing beyond risks managed through device and data security protection. This goal applies to all IoT devices that process PII or directly or indirectly impact individuals. Note that each goal builds on the previous goal and does not replace it or deny the need for it. As with any risk mitigation strategy, risk must be addressed, and if the organizations are using IoT devices in the organizations, they need to consider additional controls apart from the traditional controls that need to be implemented. So this includes taking into account IoT risk considerations, adjusting organizational policies, processes, and implementing updated risk mitigation practices. So if let's look at some of the IoT risk management areas. So if we look at device security risk mitigation areas, for example, asset management, accurate inventory of IoT devices for cyber and privacy risk management forms the baseline. If we look at data security, monitoring IoT device activity for signs of incidents involving data security. Same if we apply for privacy, monitor and analyze IoT device for signs of breaches involving individuals' privacy. So if we look at some of the real world IoT vulnerabilities, this slide depicts the real life examples of IoT product attacks by using the vulnerabilities. This is quoted from NIST white paper. As you can see, as much the applications are varied, so are the avenues for the attacks. A real life example of IoT product attack and the associated vulnerability exploits that contributed to the security incident. As with any breach, it is not possible to determine with certainty all the specific tactics and techniques used by the adversaries to exploit vulnerabilities. So, unauthorized access to fish tank thermometer enabled adversaries to reach sensitive databases and exfiltrate data. So, what are the vulnerability factors there? So, it was lack of access controls from the smart thermometer to the attached network. Devices left servers, databases, and other digital assets vulnerable through the smart thermometer. Remote access from the internet to the smart thermometer made the device and the network to which the thermometer was attached vulnerable to unauthorized remote commands. Lack of alarms or other indicators from the device about the unusual activities uh, did not alert basically the network administrators of the compromised state of the device. So if we look at device cybersecurity requirements should be based on the security capabilities and security requirements of the system and the organization, also updating the system risk assessment as necessary. So this diagram basically shows this process and how it draws information from all the relevant sections to inform the device cybersecurity requirements. So NIST IR 8259 series of reports provides guidance for manufacturers and their supporting third parties. Recognizing that IoT use cases span across many industries and there are some common capabilities, 8259A provides a core baseline. It outlines the device capabilities generally needed to support common cybersecurity controls with the goal of protecting an organization's devices, data, systems, and ecosystems. To complement the core baseline from NIST IR 8259A, the IoT non-technical supporting capability core baseline is a set of actions performed by manufacturers and or designated supporting third parties called supporting parties. These actions will help others, example customers and users, use the cybersecurity capabilities of IoT devices and support the ongoing cybersecurity of the IoT device and the system and the networks that device connects to, that is the digital ecosystem. Providing such non-technical cybersecurity support through educational materials or other types of non-technical tools and actions can benefit the entire IoT device ecosystem, allows manufacturers to better support the cybersecurity of devices throughout the entire device lifecycle. Both device cybersecurity capabilities and non-technical supporting capabilities are vital to customers' abilities to achieve their needs and goals. Similar to IoT device cybersecurity capability core baseline in NIST IR 8259, the IoT non-technical supporting core baseline is intended to give organizations a starting point for establishing non-technical actions to support IoT device cybersecurity risk management. So if we look at the risk options, as seen in most of the cases, not all IoT devices available in the market can meet the needed device cybersecurity requirements, which does not mean that we can use the IoT device or we cannot use the IoT device. So if you look at the likely outcomes for organizations, for the first determination, an organization acknowledges the lack of a device cybersecurity requirement but accepts the deficiency. The second and third determinations involve the use of alternative capability and or security control than originally intended by the organization. The second determination is the simpler of the two since it does not require a change in security control, but rather a different capability to support the security control. Third determination involves the organization selecting a compensating security control for the information system. This compensating security control better matches the capability or capabilities provided by the IoT device while still addressing the same security goal to manage risk. For fourth determination, the IoT device cannot be used by the organization as intended because of the lack of the capability. This would be the determination if an IoT device lacks a key device cybersecurity requirement, where the organization has identified those device cybersecurity requirements that must be met. Exam that is not omitted or replaced with an alternative by an IoT device, and its manufacturer and supporting entities be considered securable by the organization. So, if the IoT device lacks technical or non-technical capabilities to support the information systems controls, challenges can arise for the organization to manage risk. In this situation, technical or non-technical capabilities lacking in an IoT device might be provided by other system elements or systems. So let's look at some of the challenges of implementing the requirements. What you're seeing on the slide is risk mitigation areas for each of the three areas: device security, data security, and individual's privacy. So if we start with a vulnerability management area, the expectation is that the device either has its own secure built-in patch, upgrade, and configuration management capabilities, or can interface with enterprise vulnerability management systems with such capabilities. The challenge could be that the IoT device may not be able to participate in a centralized vulnerability management system. So what is the implication for the organization? So the organization may have to use numerous vulnerability management systems instead of one. They may have to perform vulnerability management tasks manually and periodically. So the second column is NIST special publication 853 controls. And fourth column is example of cybersecurity subcategories that might be negatively affected by the implications. Similarly, if we look at an example for data security area, the expectation is that the device can prevent unauthorized access to all sensitive data on its storage device. The challenge could be that the IoT device may not provide sufficiently strong encryption capabilities for its stored data. And lastly, if we look at an example for informed decision making as part of protecting individuals' privacy, the expectation is that traditional interfaces exist for individual engagement with the device. The challenge could be the IoT device may lack interfaces to enable individuals to interact with it. And the implication for the organization is that the individuals may not be able to provide consent for processing of their PIA or condition further processing of specific attributes. So the last category basically omits mapping to cybersecurity framework subcategories, since cybersecurity framework does not address privacy risks from authorized PIA processing. So if we look at the ERM view, the enterprise risk management view, to get an overall understanding, if you see the holistic picture of organizational risk management strategy, the relationship of an IoT device to an information system provides the context to understand how an IoT device supports system and organizational objectives. IoT device as a system element shows how incrementally it affects the risk it brings in and how it needs to be considered as part of the risk management process. An updated risk assessment may require additional or new controls to be selected and implemented in the system. The second diagram shows how device cybersecurity capabilities and non-technical supporting capabilities grouped together as device cybersecurity requirements support the system or the organizational security capabilities, which in turn satisfy the organizational security requirements. Lastly, I would like to conclude saying that introducing IoT device brings in risks which must be carefully evaluated before integrating into the organization. So this is NIST documentation. So right from 2019 of publishing NIST 8228, IoT technology has been changing and adopted across various organizations. So far, there has been progress in consumer IoT, capabilities catalog, and IoT diversity and heterogeneity continues to be the challenge for achieving cybersecurity objectives. With this note, I thank you for attending the session. Lastly, these are the references I have used for this session. Thank you.